So chemistry is the scientific study of matter. Science is just a systematic method of observation with checks that you can test whether your theory is valid or not. And matter is anything basically that exists. If it has mass, if it occupies space, then it can be measured. That's matter. So chemistry is the scientific study of those things in the universe that we can measure because they exist. And we also look not only at the individual parts of the universe, but how they interact with each other. So because we're going to be doing some measurements, we need to talk about dimensions. And dimensions fall into two types of categories. They're either fundamental or they're derived. A fundamental dimension is something that exists in its own right. It's not subdivided into something else. So length, distance, is a fundamental unit. Mass is a fundamental dimension. Energy, temperature, and also time. For distance or length, we use the meter. Not yards, not inches, because inches and yards are not metric, whereas meters, kilometers, millimeters are, and I will show you that in just a minute. For mass, we use the gram. For energy, there's a nice convenient unit of energy called the calorie, with a very nice definition of what a calorie is. And we will use that from time to time. It's a very useful unit for nutrition. But in physical sciences, we use the joule as the unit of energy. Temperature, two temperature scales. There's the temperature scale that is Celsius, that runs from 0 to 100 degrees Celsius. That's ice to steam temperature. And then there's Kelvin. And time, our unit of time is the second. Not the minute, not the hour, because those subdivisions are subdivided by 60 and therefore not metric. Dimensions can also be derived, and a derived unit or a derived dimension is a combination of other units. So a volumes describe three-dimensional spaces. That's a length times a breadth times a height if you're thinking about a cube. So that's a distance times a distance times a distance. The distance itself is the fundamental unit. The derived unit is volume. And density, which is mass divided by volume. The way that our metric units are going to pan out is that we'll have the fundamental unit here. In this case, I'm looking at distance, so I'm using the meter. If I multiply that up, I get to the kilometer or kilometer. And so meter, represented by an M, to be converted into kilometers, 1 kilometer equals 1,000 meters. And in scientific notation, we count the number of zeros in the number and then raise our underlying number to that exponent. So 1,000 is 1 times 10 to the 3. If we subdivide the units down, what we do in science is we jump in units of 1,000. So here in the metric system of distance, you might be thinking to yourself, where's the centimeter on this list? Strangely, we don't use the centimeter because the centimeter doesn't fall into the neat description of every 1,000 units. Centimeter is a nice, convenient household type of unit, but it's not used in scientific notation. We skip over the centimeter and go to the millimeter. 1 millimeter is 1,000th of a meter. So there are 1,000 millimeters in 1 meter. And a millimeter, therefore, is 1 divided by 1,000, which is 0.001 meters in distance. It's important that you keep this 0 in your number, the 0 that is before the decimal point, because that helps us keep track of our exponent. Now, because a millimeter is less than 1, a millimeter is less than 1 meter, our exponent is a negative number. And the exponent, again, tells you the number of zeros that are in the number itself. A micrometer is 1,000th of a millimeter, which in turn means that it is 1/1,000,000th of a meter. So 1 micrometer, this symbol here is a mu in front of the meter. That's the Greek symbol mu for a micron or a micrometer. So 1 micrometer is 1 divided by 1,000,000. So it's 1/1,000,000th of a meter. And is shown as 1 times 10 to the negative 6. The negative exponent tells you this number is less than 1, and the 6 tells you that there are 6 zeros in that number. Smaller than the micrometer, 1,000th the size of a micrometer, is the nanometer. It is 1/1,000,000th the size of a meter, and it is given symbol 1 times 10 to the negative 9 meters. If we look at temperature scales, I said earlier we're going to have 2 temperature scales. The other temperature scale that you may have heard of is not used in science at all. We use either Celsius to describe things, or we use Kelvin in calculations. Celsius is a very nice scale because between the convenient numbers of 0 and 100, we have most of what human experience is, between ice temperature and steam temperature, between pretty cold and pretty hot. However, because numbers on the Celsius scale can become negative, we don't use those in calculations. If you think for a second that volume and temperature, the volume of a gas and the temperature of that gas might be proportional to one another. As the temperature goes up, the volume inside the balloon might expand and also go up. So if you were using a temperature scale that allowed a negative number, that would mean that the volume would have to go negative also in your calculation, which is an impossible thing because the volume is a number times a number times another number. There's no such thing as a negative volume. So that's where Kelvin comes in. Kelvin always stays positive, and it's the temperature scale that we use exclusively in our calculations. Fortunately, the Kelvin scale and the Celsius scale are in lockstep when it comes to degree changes, so that a 1 degree change in Celsius is also a 1 degree change in Kelvin. What Kelvin does is it gives us the concept down here, cold at negative 273 degrees Celsius, of something called absolute zero. At absolute zero, our sample has lost all of its thermal energy, which means it has no more energy left to give out to the environment. Therefore, it cannot physically get any colder. We'll look briefly at 2 types of sources of error in measurement. Errors in measurement can either be systematic. That means that there's an error in the way that a procedure is performed or that an experiment is designed. So just thinking of something mundane, if you were keeping track of your weight and you weighed yourself every day, but you weighed yourself while you were brushing your teeth, then you would be weighing yourself plus the toothbrush. Now that's a very, very minor error, but it would be the same error over and over. What if you had a coffee mug in your hand every morning when you stepped on the scale? Then you would be measuring your own weight plus the weight of the coffee every single morning. So every single piece of data that you had would be skewed the same way. That's a systematic error. Systematic errors are also called bias. The other type of error that we worry about less in design is random errors, because random errors are by nature random, and that means that they're very difficult to predict, and that the numbers or the results that they throw up are unpredictable. And so over the course of time, if I take lots and lots of pieces of information, over time, randomness should average to 0. So random error is not really something that I have to worry about. Systematic errors, much more of a concern.